Okay, let me begin here. Part 3 of the screencast on cosmology. Let me pick up where I left off at the end of part 2. I was giving you some more details here of the universe's space-time diagram. So as I indicated at the end of part 2, this is overall describing the shape of the universe, if you will. I specifically mentioned dark energy at the end of part 2. Dark energy, about 5.5 billion years ago, kind of was like an inflection point, if you will, where the rate of expansion went from a decelerating expansion prior to that to an accelerating expansion afterwards. We don't know why the universe is expanding at an accelerating rate. We have a name for this cause. It's just simply caused dark energy, but we don't know exactly what it is. Okay, a few other details here on this diagram before I move back to the slideshow. So as I indicated earlier, we go back in time from right to left here on the diagram, and then here are some of the more powerful examples of telescopes that we have used to explore the universe in its distant past. So I mentioned COBE and WMAP exploring all the way back to a time here, 380,000 years after the Big Bang itself, when the universe becomes transparent. This is then where the cosmic microwave background originates from. Okay, now the Hubble Space Telescope. The Hubble Space Telescope back in the late 1990s and early 2000s was basically pushed to its extreme. Basically what they did with the telescope was they used the telescope to focus in on a single point in the sky, and then they looked continuously at that point for several weeks, collecting all of the light that they could from early in the history of the universe. It basically looked back to a time roughly here on this diagram, just after the formation of the first stars and the formation of the first galaxies. I'll show you some pictures of this in the slideshow in a little while. What the Hubble Space Telescope, however, is not able to do, it's just simply not big enough. It's not able to look back into a point in the early history of the universe that's referred to as the Dark Ages. The Dark Ages is basically the point after the cosmic microwave background, so the universe is transparent, and then the first stars begin to form. We still haven't seen those stars as of yet. The Hubble Space Telescope, frankly, is not powerful enough to look back into this period of time. The next generation space telescope, which has been built, it's called the James Webb Space Telescope. It will be launched in early 2021. In part, it's designed to look back into this period of time here, early in the history of the universe, called the Dark Ages. See the formations of the first stars, see the formations of the first galaxies. A few other highlights appear here on this diagram as well. This point in space right here, or point in time, I guess I should say, which dates back to about 400 million years or so after the Big Bang itself. That's the period of time where galaxies begin to form, supermassive black holes begin to form at the cores of those galaxies, and then time goes forwards from there. If we look back to a period of time here, we're looking back to a period of time of billions of years in the past where there were quasars. Quasars are extremely active galactic nuclei, where you have a huge amount of matter pouring down the drain of extremely massive black holes. Okay, the Dragon of M87, the massive black hole at the center of M87, was probably a quasar in the past, but it's not as active today as the quasars that we see in the distant past. Today in the universe, there are no quasars, and then today we see nice mature galaxies. This is kind of like a diagram describing more or less the large-scale history of the universe from the time, for example, of today, going all the way back to the cosmic microwave background. Later on in the screencast, I'll begin to explore what is happening over here on the left-hand side of this diagram. All right, getting back to my slideshow from earlier, let me go ahead and start it from this point here, like so. So I mentioned the accelerating rate of expansion of the universe. This discovery was made in 1998, and it led to a Nobel Prize in 2012. This right here is a graph, exactly as the graph that I described earlier that led to the discovery of the Hubble constant. We have a plot here of the recessional redshift velocity of galaxies as a function of distance. Now, the closer you are to the origin on this map, the closer you are to this moment in time. So then therefore, when you look further along the horizontal axis here in terms of distance, you are looking further back in time. Notice how the slope of the line tangent to this curve has changed over time. So if you go back to the distant past, very far out into the early history of the universe, Notice that the slope of the line tangent to the curve here on this graph is less than it is today. And remember that the slope of this line ultimately describes the rate of expansion. So the rate of expansion in the past was less than it is today. This is the accelerating expansion of the universe that we have discovered that is going on today. We don't know the cause of this. We simply have a name for it, and we refer to it as dark energy. So that's where I was, more or less, at the end of the second part of this screencast. Okay, now I'm going to kind of switch gears. What's going on before, for example, the cosmic microwave background was released through the universe 380,000 years prior to the, or excuse me, after the Big Bang. Now, we can't explore that region of the universe because basically 380,000 years after the Big Bang, that's the point where the universe becomes cool enough to become transparent. So it's opaque. Earlier than that, our telescopes cannot see into that region of the universe. So how do we explore that region of the universe? We explore that region of the universe through particle physics. Now, I have previously described in class what is meant by the Standard Model. The Standard Model of particle physics, developed from the 1920s forward until about the 1990s, is basically our current understanding of three of the forces that occur in nature. The two types of nuclear forces, strong and weak, and the force of electromagnetism. Those three forces occur at extremely small scales, and ultimately the particles that get sprayed out in particle collisions and particle collision experiments, ultimately those particles are basically describing the mathematical properties of those three forces. Collectively, the theory itself is referred to as the Standard Model. Okay, now let me go ahead and skip to this diagram here in my slideshow. And this diagram here in my slideshow also corresponds to a picture that I always draw on the board for everybody at this point. Let me go ahead and switch to that as well. There we go. That's this right here. What you're looking at here is basically the very early history of the universe from the point, the initial point of creation, all the way to today, but then also here on this diagram, this point here in the early history of the universe, 380,000 years after the Big Bang itself, when the universe became transparent enough for the cosmic microwave background to be released. Okay, we have four forces, the four fundamental forces that exist in nature that are being described here on this diagram. We have the strong nuclear force here, the weak nuclear force, the force of electromagnetism, and our current understanding of gravity, general relativity. Today, in the very cool universe, these four forces are distinct from one another. But the Standard Model shows, and particle collision experiments show, that if you start to move backward in time, the universe gets hotter and hotter and hotter, and it becomes more and more dense. If the temperature is hot enough, what we discovered in these experiments is that the weak nuclear force and the force of electromagnetism combine together. They combine together to become what is called the electroweak force. So when the temperature of the universe is in this region right here, there are actually only three forces that exist in nature: general relativity, the electroweak as it's called, and the strong nuclear force. This right here is basically the realm, if you will, of the Standard Model of particle physics as we understand it today. Okay, now presumably this unification process of merging together the four forces continues into the early history of the universe as the universe gets smaller and smaller and it gets hotter and hotter. It's been hypothesized that if the universe is hot enough, you can then merge together the strong nuclear force and the electroweak force into a single force that is called the Grand Unified Theory. The Grand Unified Theory has never been observed in any particle physics experiments. We do not, as of yet, have a good understanding of the mathematics of a Grand Unified Theory. But then, if you run the movie back even further from that, then the Grand Unified Theory may in fact merge together with general relativity to produce then a single theory of nature, what is sometimes just generically referred to as quantum gravity. Our best bet, our best candidate for a theory of quantum gravity right now is what is called string theory. I've described that, for example, in class. Okay, now let me give you an understanding here as to what exactly it is that you're seeing on the diagram in terms of events, if you will. So we have, first of all, the moment of creation itself. From the moment of creation to a time of 10 to the minus 43 seconds after the Big Bang itself, when the temperature of the universe was 10 to the 30th degrees Kelvin, we do not have our current understanding of physics explain this realm of the universe. The reason why is because we don't have a theory that merges together the four forces into a single theory, that of quantum gravity. Now, exactly why is it 10 to the minus 43 seconds? I've mentioned this number in class, but why is this number so important when it comes to the early history of the universe? Let me go back to this slideshow. I'm going to go to this slide here. Okay, the smallest meaningful distance in physics is called the Planck length. It's a combination of fundamental constants that comes from quantum mechanics. The Planck length is equal to a size that is 10 to the minus 20th the size of a proton. Now, the speed of light. The speed of light is a fixed constant of 3 times 10 to the 8th meters per second. The Planck length itself is 10 to the minus 33 centimeters. That's 10 to the minus 35 meters. It takes light 10 to the minus 43 seconds to cross the universe if the universe was that distance. So that's the meaning of what is called the Planck time. The Planck time is the smallest meaningful moment in time based upon our current understanding of the standard model of particle physics. So we have a pretty good understanding as to what has happened in the universe from this point, 10 to the minus 43 seconds after the Big Bang forwards, but we have zero understanding of what happened beforehand, because this is basically where our understanding of the standard model ends. That's why that number is so important. Okay, let me exit out of this. There we go. Let me go ahead and go back to the diagram, like so. Here we go. Okay, so basically our meaningful physics more or less begins right here. And then from this point forward, the universe expands and it cools. As it expands and cools, then the forces split apart from each other to become the four distinct forces that we see today. This diagram right here is referred to, by the way, as broken symmetry. Okay, now 10 to the minus 43 seconds to about 10 to the minus 35 seconds. We believe the following happened in this extremely short period of time. The universe increased in size by 26 orders of magnitude from this moment in time to this moment in time, and it cooled down from this temperature to this temperature as it did. Now, 26 orders of magnitude, what does that mean? Well, an increase of 2 orders of magnitude would be an increase by 100. An increase in 3 orders of magnitude would be by 1,000, and so on and so on. So imagine that the universe at this moment in time is 10 to the minus 35 meters wide. And then what you do in an extremely short period of time here is you basically inflate the universe to an enormous size. You increase its size by 26 orders of magnitude. Now, to give you an understanding as to exactly how big 26 orders of magnitude is, consider the following. Take a basketball, and then in an extremely short period of time from here to here, increase the basketball's size by 26 orders of magnitude. How big is it when you do? It's bigger than the Milky Way galaxy. So in other words, this is basically the bang. This is the bang of the Big Bang theory of cosmology, when the universe expanded at an enormous rate over an extremely short period of time, very early in the history of the universe. And then the rate of expansion has slowed down since. It is, however, since accelerated from 5.5 billion years ago, as we've discovered with dark energy. So begin to think of the Big Bang theory of cosmology in the following manner. Don't think of it really as a theory of the creation of the universe. That's not quite true. Instead, it's a theory of the expansion of the universe that happened after the moment of creation. So in other words, we've got a pretty good understanding as to what happened in the universe from this point here, 10 to the minus 43 seconds after the Big Bang itself, all the way to the present day. Now I'm going to have to pause this lecture here and continue with a part 4 in just a few minutes.